Alright, so I did the following. I went to process and I did a rerun all, which ran everything, and I re-uploaded, and that actually seems to work. So, so here's our FPGA. Let me kill the lights here. So a little hard to see, but I've got 2 LEDs on and 2 off, right? So, remember, our switches look like this, which means if I don't press the switch, what's the logic level going in? To logic 1. So with no switches pressed, this is a 3, this is a 3. 3 times 3 is 9. That's 1, 0, 0, 1. So that's 3 times 3. So if I press all the switches, that's 0 times 0, all my LEDs are off. If I release those first 2, right, that's 1 times 1 is 1. There's 1 times 3 is 3, there's 1 times 2. Here's 2 times 2 is 4, 2 times 3 is 6, 2 times 1 is 2, and 3 times 3 is 9. So that's a multiplier, right? So I don't know why I had to rerun, but like I said, I did a rerun all, and...
So what did you rerun?
So...
Like the first time, what was it that you ran that didn't work?
So the first time I did the whole synthesis, right, so we could look at the schematics, and then I added a constraint file, and then I clicked on this arrow again to run it. And I think it didn't rebuild some things that should have been rebuilt, maybe. So I came up here to process and I said rerun all. And that time it magically worked. So let's make one change and see if we can still get it to work. So I'm going to make some things called A true and B true. And these are going to be the values that I actually wanted to input, so that when I push a button it's a 1, when I release it it's a 0. So A true and B true will be the complemented versions of A and B. So I'm just going to do this the kind of Neanderthal way. So A true 0 is just the complement of A0, A true 1 is the complement of A1, and so on for B. And then I'm going to multiply A true and B true to get my product. Right, so effectively I'm taking this and I'm just sending it through an inverter. So if this was A0, this is what I'm calling A true 0. But I'm doing that in Verilog.
B true is misspelled in wire.
Oh, yeah, okay. Let's see what kind of error it gives us. You should catch that really quickly. Alright, lots of errors. So pick the first error and click on that, and it brings you pretty close. So B true 1, it's not actually where I'd like it. Okay, but it tells you B true is not declared, so then you can go back up and find the problem there. Okay, so I'm going to rerun all. Let's see if this works. If it doesn't, I'm not going to spend too much time fighting it. There's an appendix on this document. Problem avoidance hints. So things that will minimize the chance of getting into trouble. We have this in 270 also. There's usually hard-earned wisdom somewhere on Canvas. And it's just things that the documentation may not say, but that seem to be good to keep in mind. Alright, so this is run, place and route completed successfully. I don't think it did the programming file. So I'm going to go ahead and do that. Well, that's weird. Alright, so got all the way through generate programming file. That's all good. So let's just try programming the board. Let's see if this works. Alright, it thinks it's done. Let's see what we got. So no LEDs are on, so we can do 1 times 0, 0, 1 times 1, there's a 1. 1 times 2 is 2, 2 times 2 is 4. 2 times 3 is 6, and 3 times 3 is 9. So we got a multiplier. And it was a lot of work to get that first version working, right? To make that second change where we just complemented the inputs, minimal amount of effort. It was really just a few edits, and then just saying rerun all, and then re-executing this to reprogram the board. So it can take a lot of effort to get to that point, but once you're there and you're trying to debug your circuit or modify it or build on it, it's pretty quick, right? And this is certainly going to be faster than putting wires into a proto board and finding chips and things like that. So that's basically the whole tool chain, right? Now if you're working with a board like this, right? It's a different chip. It's a Spartan 3, and it has a different package. So different family, different part number and package, but you put those in the beginning, and different pin numbers, right? If I want to connect to these switches here, they're going to be different pin numbers, but I find the documentation for this, and I put those in my configuration file. The rest of the process is identical.
Which is it there?
This one, oh, I don't know. I would guess maybe 96. That's just a random guess though, but it sounds good. So when you start with a new board, you always have to find the documentation, and sometimes you have to find it online, right? Usually this is what you get from a vendor. But once you've programmed a few of these, right, the process of switching to a new one is not all that bad. And they might be fundamentally different devices internally, but Verilog is the way you interface with those, right? I'm always going to write something like, you know, assign output equals A times B, whatever this is going into, and all the stuff that's happening when you hit the run button is it's figuring out for this particular device, how do I translate that into what we want. And you know, we've got 4 inverters here complementing the inputs, but if we come down and we look at the schematic, we don't see extra inverters in here, right? Why? Because it just modified the lookup tables. The way that these got implemented were adjusted so that it used the inverse of A0, B0, A1, B1, right? And so there's implicit inversion taking place, but it's figuring out how to do that for you. So any comments or thoughts or questions about all of this? FPGAs, Verilog, programmable logic. You're obviously not going to have to know the details of programming the board and using the Xilinx tools and stuff like that for the exam, right? You're going to be tested on basic Verilog, and we'll spend Thursday going through review for the exam in general.
But is 270 cover more of this, or?
No, this unfortunately is the only time that you'll see this here, and it's, if you're computer science, it's probably the only time you'll see it for a few years, because it's just not usually a part of a CS curriculum. If you're electrical engineering, you may bump into it in higher level courses, but it's pretty easy to work with on your own now, right? It used to be these boards were ridiculously expensive and the software was expensive, and you needed a server to be able to run it. And now, you know, you can get a board for 30, 40 bucks from Amazon. The software is free. You can run it on a laptop. But it's probably not something you'll find in courses, and definitely not in 270. It's not uncommon to find FPGAs that have microprocessors on board, though. Right, and so some of the stuff we do in 270 you might be able to do actually on part of, you know, one of these chips, or as I said last time, you can actually get Verilog for a whole CPU and dump that in to your chip and build yourself a little standalone microprocessor inside that you write programs for, and you use that to interact with circuitry that you're building. See how much trouble we can get into in a few minutes. So Spartan 6, like I say, that's a affordable family of FPGAs from Xilinx. Xilinx is one of the two main players, along with Altera/Intel. So this summarizes the different types of FPGAs available in the Spartan 6 family. So general features of them, right? Block RAM, so they actually have random access memory inside that you can tap into. Blocks for controlling memory for interfacing with, say, DDR2 memory like you have in your laptop. Works with a variety of voltage levels, has should have some multipliers built onto the chip to actually do long number multiplication. And here's the different families, different models you can get. So main feature is the number of logic cells. How many different blocks can you program inside the device? So I forget what the number was on this one. 6LS, anybody remember what it was?
X9.
9, okay, so 9,000 logic cells, right? Pretty much on the low end of it. On the high end, you got 150,000 programmable cells, and it's just how big of a circuit you can put into your device. And it's organized in different ways, but for example, the top end, 184,000 flip-flops. Ours has a meager 11,000 flip-flops inside available. Distributed memory, 90K up to 1.3 meg, and so on and so forth. Also the number of user I/O, right? So how many ports can you connect to? So 200 I/O lines that we can get to on our SLX9. The biggest device, 540 I/O lines. So depending on what you want to control with it. find lots of wordage that you can read. I'm looking for a picture. Nope, no picture here. But there's how you read what the part number is. Right, so device type, speed grade, temperature range, number of pins, and so on and so forth. And Xilinx has just this ridiculous number of different devices available. Right, these are just the ones from the Spartan 6 line, but lots of other options. And I think this one will have a picture I'm looking for. Oh, this is the marketing kit. Let's try one more. That's the same. All right, I'm not going to spend time looking for it, but you can dig into here, right? There's a whole multi-hundred-page data sheet for each of these devices, and it will show you what the combinational block looks like inside, and it's basically a little lookup table, okay, something like a multiplexer that we can use to generate random logic, right, by setting ones and zeros on the inputs, like we've done. Usually a few flip-flops on the output side, some feedback so that we can make sequential circuits out of these. And then in between each of these logic blocks, whole bunch of wires. And by setting multiplexers, we can connect outputs of one block to inputs of another block. And we can basically control the routing of inputs and outputs throughout the FPGA by just setting up the inputs to multiplexers. And that's what most of the space inside these devices is just wiring, just routing to connect things together. And part of what the software is doing is figuring out the optimal way to route it in terms of speed and power and so on and so forth. And that's different from chip to chip. And the way that you actually load in the ones and zeros to set up particular routing and so on, that's all secret. All right, that's all closed proprietary information for the vendor. Which is why we can't write our own software to program FPGAs, so you have to use software from the vendor or someone working with the vendor. But all the other information other than that level of detail is in these data sheets. All right, so let's get rid of all of that. All right, so if you're interested in playing more with this, we have a bunch of these available in one of the back rooms. And like I say, when you're thinking service learning project, FPGAs can be a fun way to play with things. I'm going to bring on a little bit of light. Any other questions, comments? So my plan was to post a study guide for the final, probably today or tomorrow, and then go through that on Thursday. I don't think we need more than one class time to go through that. But any questions you have right now that you want to talk about from anything that we've done? Otherwise, I'm just going to talk about high-speed math and ways that we do high-speed math on digital systems, and it's not part of the exam. You won't be responsible for it, but it's something you'll probably see later on, and I think it's a cool area. It's like making arithmetic quicker. But any questions or things you want to go over first?
Would it hurt if we kind of like reviewed how to like map a fuse map?
Sure. I mean, sure, we can do that. Not sure it would hurt. So programmable devices. We have this way that we normally draw circuits, right, when we're trying to be neat. Where we have inputs and we complement them and we run these vertically. So I don't know, maybe this is A, B, C. And we want to compute product terms if we're doing a sum of products. So we'd like to take a wire from, say, A and B bar and C bar and put that into an AND gate, right? And if we're using an FPGA and we're drawing a fuse map, the way that the connection should be drawn, we use a shortcut, which is we just draw a single wire, and we're going to draw an X where we want a connection. And we have to understand that there's multiple wires going into this AND gate, and if we have an X here and an X here, it means we have one wire coming from this line A bar and one wire coming from this line B bar going into our AND gate. Okay, so it's a shorthand, so we can have a series of these. And these are all ANDs. So those are product terms. And then we want a sum of those, which means we want to take some collection of those products and OR them together. And so again, we use this shorthand where we just run a single wire into an OR gate. And we might have multiple outputs. So we could have something like this. And I don't know, let's call this F, G, and H. So suppose we want to implement the following function. F equals A bar B or B bar C or AC. And maybe just G equals AC. All right, so work with one output at a time. Let's just work with F. And it's a sum of three products, so let's generate each of those products one at a time. The first product we want is A bar B. Well, here's an AND gate. AND gates generate products. So let's make a connection to A bar and another connection to B. And so the output on this line is A bar B, and I might label that. That's not technically part of the fuse map, but just for me to keep it straight, I'm going to put a little label there and say this is A bar B. And then I also want the product term B bar C, so I'm going to make a connection between B bar and the second wire, and a connection between C and this wire. And so the output of this AND gate will be B bar ANDed with C. And then the third one, I would make a connection to A and C, and the output here will be AC. And now I want F to be the OR of these three terms, so I'm just going to take those three product terms and feed them into my OR gate. There's my whole fuse map for F. G conveniently just wants to be A ANDed with C, so I'll just take that one product term and run that through my OR gate, and so now G is equal to AC, and so on. So that's just a shorthand of how we would normally draw a circuit, where we'd have a bunch of wires going into AND gates and we put dots to show that they're connected. But in the actual hardware, right, you've got the AND gates, you've got the OR gates, you've got multiple wires, and you've got these connections between vertical and horizontal that we can cause to break. We can melt them like fuses. And the ones that we don't melt remain connected. That's what we're showing by the X's. And so it's just implementing our circuit. Does that help? Cool. Let's talk about addition. So we know how to add numbers with pencil and paper. Right? Start with the rightmost number, add up all the numbers in that column, write down the last digit from that sum, and then carry the other digit to the next column. Add up all of those, including the carry, write down the rightmost digit, carry the next column, and so on. Right? In binary, your carry is a single bit. So if we're doing something like this, right? 0 and 1 is 1 with a carry of 0. 0, 1, 0 is 1 with a carry of 0. 0 plus 1 is 2, which is actually 0 with a carry of 1. And then 1 plus 0 is 1, and so on. We may as well finish this up. So that's a 0, and that's a 0, and that's a 0, and then there's an extra carry out at the very end of a 1. Okay, and this is a ripple carry adder. Because we didn't know that we had a 1 over here at the very end until we had added up all these bits to the right of it. And it wasn't until we did this last 0 plus 1 plus that extra incoming carry of 1 that we saw we're going to have a carry coming out. So if we had 1,000,000 bits that we were adding to 1,000,000 other bits, we might have to wait 1,000,000 propagation delays until we know what that last carry is. And it might be a 0 all the way until the very end of the 1,000,000th propagation delay when this last one has trickled over, right? So that's fairly slow. And that can be a problem. So people have spent a lot of time trying to speed up arithmetic. And the most basic part of arithmetic is addition. So if you can speed up addition, you can speed up multiplication, because multiplication is just a bunch of additions, right? You multiply bit by bit, and then you have to add up all these numbers. So getting rid of this ripple carry effect is key to speed up. So one way to do this is to do what's called a carry look ahead. So this is a ripple carry adder. Okay, a carry look ahead adder figures out what the carry is before it's had a chance to ripple across. And I'll give you the 5-minute version of this. This is normally like 1 or 2 classes of lecture in a computer architecture course. But we'll do the short version of this because it's not on the exam. But just to kind of give you an idea. Basically, we've got, you know, we've got some part of our addition that we're performing. And we've got, I don't know, let's just look at bit 5, right? So we've got bit A5 and bit B5 that we're adding up. And we've got some carry that we're also adding into that, which might be a 0 or might be a 1. Okay. The question is, when does this addition generate a carry into the next stage? So, say again?
I'll say when enter B or 1, then generates a carry.
Okay. So, so carry is generated if A equals 1 and B equals 1. Is there any other case where we might get a carry going into this next stage?
The other carry is also a 1.
Yeah, if the other carry is also a 1, and what else?
One of the others is a 1.
And one of the others is a 1. Okay, so a carry is generated if A is 1 and B is 1. We can say a carry is propagated if A equals 1 or B equals 1. In other words, if one of these bits is a 1, if there's an incoming carry, that'll get propagated to an outgoing carry. So there's 2 cases where we can have a carry generated, where we can have a carry going into the next stage. Either we generate one because both of our bits are 1, or maybe only one of our bits is 1, but we also have a carry coming in. So we can start writing some math gobbledygook that will get us somewhere. So carry out of stage 0 is A0 ANDed with B0. They both have to be 1. And I'm going to call that generate 0. I'm going to say that bit 0 of my numbers is going to generate an outgoing carry. Okay, adding my second bit position, position 1, will generate a carry if A1 is 1 and B1 is a 1. It will propagate a carry if A1 is a 1 or B1 is a 1. And the carry out of bit position 1 will be true in the following cases, either because it's generating it or because it's propagating and it had an incoming carry. So this is the outgoing carry from bit 0, that's the incoming carry to bit 1. So bit 1 generates an outgoing carry if it generates a carry itself or it propagates a carry and there's a carry coming in. And now we can just go to town. Stage 2 will generate a carry if bits 2 are both a 1. It will propagate a carry if either of those bits is a 1. And the output from stage 2 will be a 1 if it either generated a carry or it propagated a carry and the incoming bit was a 1. Which we can write as G2 or P2, and for C1 we can replace that with G1 or P1C0. And each of these things is just a simple AND or a simple OR. And we can keep going. And if we have an 8-bit adder, we can figure out what the carry out of the 8th bit is, and it's going to be G8 or P8C7. And C7 is going to be G7 or P7C6, right? And we can write a single Boolean expression for each of our carry bits. Now the logic for this is long, right? But we can write this as a single sum of products. Sum of products, how many propagation delays does it take to do any sum of products expression? I don't know if we've actually talked about this, but where's our... Right, whatever this expression is, you set up your inputs, it has to go through an AND gate. That takes a propagation delay. All of these AND gates fire at the same time, and then all of those outputs have to go through an OR gate. That's a second propagation delay. It's a total of 2 propagation delays. So if your AND gate takes 5 nanoseconds and your OR gate takes 5 nanoseconds, 10 nanoseconds to find this expression, no matter how complex it is. Which means we can generate each of these carries, in this case, in 10 nanoseconds. As opposed to doing a ripple carry where it takes you 10 nanoseconds to find the first digit, and then 10 to find the second, and then 10 to find the third, and after 80 nanoseconds you get your final carry out. So this is throwing hardware at the problem. It's making it run quicker, but it takes more resource, more physical stuff. Which also means more power, more space, more heat generation, and so on. But that's a carry look-ahead adder. And it's basically using some Boolean algebra magic to figure out what the carries are ahead of time. So hold that in mind, and let me show you the even cooler version of this. Which is called a carry save adder. So suppose I want to add these numbers together. Yeah, we can add 1 and 1 is 0, we can ripple a carry over, and so on and so forth. That works. There's something else we can do. We can generate 2 sums from this. The first one, we're not going to worry about carries. We're just going to add our 2 bits and write down what the corresponding digit is from the sum. 1 plus 1 is a 0. We're not going to worry about the carry. 0 plus 1 is a 1. 1 plus 1 is a 0. 1 plus 1 is a 0. 1 and 0 is 1. 0, 0 is 0. 0, 1 is 1. 1 and 1 is 0. That's completely ignoring the carry bits.
like what's it called, a XOR gate?
A what?
A exclusive OR gate, because it did a 1 to 1
Yeah.
0.
Yeah, that's just an XOR, you're right. Because if it's 2 zeros or 2 ones, you get a 0, otherwise you get a 1. All right, we're going to generate another number, which is just the carries. And we're not going to worry about the sum bit. So 1 and 1, that generates a carry. 0 and 1 does not. 1 and 1 does, 1 and 1 does. 1 and 0 does not, 0, 0, that doesn't, and that does. And this is just an AND gate, right? If you have 2 ones, that generates a carry, otherwise it doesn't. So XORs for this, ANDs for this. Okay, well that doesn't tell us what the sum of our two numbers are, but if we were to do the following, if we were to take this number, and we were to take this number, shift it over one spot, and add those together using a traditional adder, we should get the sum of our two numbers. Right? All we're doing is we're saving the addition of these carries until later on. This thing that I've called carries is basically the little ones and zeros that you write above there. Right? But first we're adding the two numbers together and just writing the sum part, and then later on we're going to add in that carry part. Okay, now there's no clear reason for doing this yet, because we're actually doing more work like this. But when we start multiplying numbers, this is going to be the key to doing fast multiplication. And so you can tell your friends you studied Wallace trees at Clark, and they should be impressed. So a Wallace tree is a way to do fast multiplication using carry-save adders. And here's the idea. You've got two numbers you want to multiply. So pencil and paper multiplication, right? What do? You take your first number, you multiply by this digit, and you write it down. Take your number and multiply by the second digit, write it down one spot over, and so on. Well, this is easy in binary. If this digit is a 1, you're multiplying this by 1, you just get that original number back. If this digit is a 0, you're multiplying it by 0, you just get a 0. So these partial products are either your original number on top or they're just a 0. And it just depends what the bits are in this thing that you're multiplying by. So calculating those, trivial. I'm not going to do anything with these, I just like writing them. And there's all these extra zeros on the end. And there's zeros in the beginning. So we're trying to multiply two big integers. Coming up with these numbers is just a multiplexer, or maybe it's just an AND gate, right? Just take this bit, AND it with each of these, and you get either the number or you get a 0. The whole trick to multiplication is you've got all these numbers now that you have to add together. And that's a lot of work, right? So if we use our carry save adder, we end up actually doing less work than just going through these and adding them up together. And so let me just give you an idea of how this works. Suppose you have 6 numbers that you want to add together. Okay, so you can add the first 2 and then add the third and then add the fourth and add the fifth and then add the sixth. And that takes a certain amount of time. Well, imagine a building block that can add 3 numbers together. Sorry, 3 numbers together. So this is a block, and these things, we can think of them as a single bit, but they could actually be, 16-bit buses, right? But let's just think of them as a single bit right now. This is going to take in 3 bits. It's going to produce a sum and a carry. Okay, that's our famous full adder. Nothing more complex than that. So suppose you have 6 numbers you want to add together, A, B, C, D, E, F. All right, here's what we can do. Take 3 of your numbers, put them into your full adder, and again, think of these as buses, so these are, say 16 bits each. All right, so this is going to add all these bits together in parallel. This is going to add all these bits together in parallel. These are going to execute at the same time, right? So at the same time, we're going to get out a carry and a sum and a carry and a sum. And remember, these are carry save adders. So they're not actually giving us the sum of their inputs. They're giving us a sum that has to be added to the carries, right? So we don't have our final answer yet, A plus B plus C plus D plus E plus F. We have 4 numbers that have to get added together to give us our final answer. Well, we can take, say, these 3 numbers, put them into a carry save adder, and generate a carry and a sum. And then we can take the output of the carry and the save from that, and say the sum from here, put that into a carry save adder, and get out a carry and a sum. And this can go into a traditional carry look-ahead adder and generate our sum. And in terms of propagation delays, 1, 2, 3, 4 additions instead of 6. So that's like 50% faster. 33% faster. And this is logarithmic. If you were trying to add 1,000 numbers, you would end up with on the order of 10 additions instead of 1,000. Right? So the more things you're trying to add, the bigger the payoff for this. Now, if you're multiplying 32-bit numbers, integers, you end up with 32 partial products that you have to add. So 32 additions, long propagation delay, Wallace tree, 5 or 6 additions, significantly faster. And that's a key. I mean, every processor out there uses some version of a Wallace tree or something similar inside the CPU to do multiplication. And it's just one of these speed ups that goes way back into like the 50s, the 60s, the days of Big Iron, when IBM and Control Data Corporation and Cray and so on were making their room-sized machines. These were the kinds of things that they were doing in their processors to speed them up. And it's why some of these machines from CDC and some of the architectures Seymour Cray came up with and so on were so blazingly fast. And there's tons of stuff like this that goes on inside CPUs. And a lot of this stuff goes on in our processors today. Part of why Intel processors have, hundreds of millions of transistors inside is because they've got amazingly sophisticated circuitry for doing things like arithmetic. In 270, we'll extend this and talk about floating point numbers, because this is great for real numbers, right? But how do you represent this is great for integers, but how do you represent a real number like pi, right, which is 3.14? Doesn't work with just weighted positional notation. So we have positive integers, negative integers like this, but to do floating point, we need a different way to code them. And we'll go through that in 270. So that's not on the exam, but it's something I want you to have seen, because in a computer architecture course you'll come across these and you can spend a few weeks talking about fast arithmetic. And there's lots of things like this. There's an algorithm called Booth's algorithm, which is useful if you're multiplying something by, say, this. Well, if you're multiplying by a 1, we know we just take this number and we write it down, right? We've got a whole bunch of 1s in here, which is going to give us a whole bunch of partial products. But suppose this part of our number was just a little bit bigger, so that it looked like this, right? This is a really easy number to multiply by because you've only got 3 1s in there. You're only going to get 3 non-zero partial products to add together. Well, our number is this. It's not this nice simple form like this. It's got a bunch of 1s, but it's almost this nice clean form. We can pretend that it actually looks like this, multiply by this number, and then just do 1 subtraction to take off 1 more of these things because the thing we were going to multiply was actually 1 less than this. That's what Booth's algorithm builds on. And it works great if you have a pattern of 1s sitting side by side. And so there's all kinds of tricks like this for speeding things up. And this is part of a larger theme that I'm going to end with. Computer architecture, my architecture professor described it as the n-way teeter-totter. So, you know, a regular teeter-totter seesaw, you sit on one side, the other side goes up. You sit on that side, first side goes up. Well, picture some weird version of that where there's like 20 planks, right, all connected somehow. And anytime you sit on one, all the other ones go up. And if you put a little weight on one of these, it'll go down a bit, but the others will rise up a little bit. That's what computer architecture is. So what's your ideal processor? You want it to be fast, you want it to be cheap, you want it to be small, you want it to be low power, you want it to be powerful, you want it to be reliable, you want it to be easy to use, and probably some other things if you just say, give me your Christmas list or your wish list, right? And the problem is, almost any of these, if you improve, all the others get worse. If you make your processor faster, it's going to be more expensive, probably larger, definitely take more power, right? Probably less reliable because it'll run hotter. If you make it easier to use, it's probably not going to be as fast, right? And it's probably not going to be as small because if it's able to do more things that we wanted to do, it's got to have more hardware inside to translate that into hardware. And so these things all kind of fight against each other. And a lot of computer architecture is really finding the sweet spot. And it depends what your customer wants, right? If you're building a processor for a cell phone, we don't really care how easy it is to program because we can hire people to program it. We definitely want it to be reliable. It may not need to be powerful. Depends how smart we want the phone to be. Definitely want it to be low power, right? Because it's got to run off a battery. Small, maybe not, right? Cell phones are pretty dang big today. So we can probably get away with that. Cheap? No, we'll charge them $700. They'll pay for that, no problem. And probably not too worried about speed because most people are doing things that involve human interaction, so we're the slower part of the process. If you're building a supercomputer for the government, right, they don't care if that fills a room, doesn't have to be small. They can build a generator, right? Google builds their own power plants to drive their server farms, but definitely has to be powerful. Reliable? I don't know, maybe we'll build 3 of them, and when one of them goes down, we'll just switch to the other 2. Right? So it really depends on what your needs are, and it can land you all over the design space. And understanding how these affect each other and how to push yourself in one direction or another, that's part of computer architecture. And it's a really fun area that requires, you know, everything that you've learned in here, everything you'll learn in 270, and more an understanding of programming, right, an understanding of how this stuff gets used from the software side. Even if you're just building hardware, you got to understand the software side. And if you're just writing programs, increasingly, you still have to understand a lot about the hardware side to be able to write programs that are efficient. So it's all kind of blurred together, and that can be wonderful or terrifying, or both. All right, so that's a half a course worth of information in an hour. Let me leave it there, and Thursday, I'll post a study guide today or tomorrow, and Thursday we'll just kind of go through that. But if you have particular questions, particular things that you're wanting to see, ask those questions Thursday, and we'll go through those first. Otherwise, we'll just kind of go start to finish and review everything we've done. All right, and don't forget extra credit, 3 o'clock, student service learning projects, if you want to go see those. Get a yellow sheet, get some signatures, and see some cool projects. So hopefully I'll see you there.